chemical reaction that we do in that same calorimeter from the previous video will yield the same temperature change. And that's because different reactants with different potential energies are going to release or absorb different amounts of energy to the overall net equation or system. Each substance that's involved in that system releases or absorbs a certain amount of energy per mole as it gets consumed, or in other cases, as it gets produced. And to find out how much enthalpy each reactant contributes to the entire system, we measure what is called the molar enthalpy change of reaction. That is, what enthalpy change does the substance experience per mole of it being consumed or produced? Long story short, as a substance goes through a chemical reaction and experiences changes, how much energy is it dishing out or absorbing? This is called the molar enthalpy of reaction, and we can assess it in various ways. This video will look at how to do that using calorimetry data. So in our first example, we have 3.0 grams of ammonium nitrate dissolved in 150 milliliters of water in a calorimeter. If the temperature of the solution changed from 21 degrees Celsius to 17 degrees Celsius, what is the molar enthalpy of dissolution of the ammonium nitrate? So first thing is, I'd like to get my chemical formula for ammonium nitrate, and that's going to be important because I need to infer the molar mass in order to convert this here to moles. But a couple things to point out here. Remember that whenever we have a solution, we can assume the specific heat capacity and the density of water. So that 150 milliliters is really 150 grams, and we're going to write that over here, that the M is going to be 150 grams, and your specific heat capacity is 4.19 joules per gram degrees Celsius. Now, the enthalpy change of reaction has two formulas at this point in time. We use the calorimetry formula, which whenever we're given temperature changes and volumes of water or a solution, we know that this is the formula we're going to resort to at least some point in our analysis. But the other enthalpy change formula has to do with the molar enthalpy change of a specific substance as well. And that would be equal to your N for the moles of the substance multiplied by the molar enthalpy of reaction, which is given this symbol right here, this variable sign right here. And so what we could say is, since this equals delta H, and this also equals delta H, and enthalpy change is enthalpy change, then we can say that N, the moles multiplied by the molar enthalpy of reaction, is also equal to the negative MC delta T. And we can often use this key formula here to help us get the molar enthalpy of reaction, this variable here, given calorimetry data. First, using all the data of the calorimeter, I plug it all in. Next, I'm going to take the grams of ammonium nitrate. I'm going to convert it to moles, and that would be 3.0 grams divided by the molar mass from the periodic table, 80.05 grams per mole. And then that gives me a value of about 0.0375 moles. So now inserting that fully into this equation, we have 0.0375 mole of ammonium nitrate multiplied by the unknown, which is the molar enthalpy of the reaction, of the dissolution. And that's going to be equal to, again, our calorimetry data from the water or the solution that was heating up. And remember that enthalpy change is only experienced by the system, so this represents the dissolution of ammonium nitrate. We end up getting a value of 67. So I'm going to just put this in here. So 67.04 kilojoules per mole. And if we're thinking significant digits, well, the lowest amount given is 2 significant digits. So we're just going to write, and it's going to be a positive 67 kilojoules per mole. Remember that positive means it's endothermic, and the fact that it cooled down, as the question indicated here, supports that it's endothermic. And so it's 67 kilojoules per mole of ammonium nitrate dissolved. Now for this question, because we have temperatures given, we know that it is going to be, once again, part calorimetry and part regular molar enthalpy of reaction. And so our go-to equation is going to be this, where the moles multiplied by the molar enthalpy of reaction. This, of course, is going to be for the system, is equal to negative MC delta T of the calorimeter, which, of course, in our situation here is going to be the solution. And what I do want to make note of here is that whenever you get a concentration and if solution is mentioned, then we can assume that this solution is mostly water, and hence it's going to then carry the density of water and the specific heat capacity of water. So these volumes here that are given, you can treat them like we're giving you volumes of water, and so they can be additive or added together. So if I'm going to fill this equation out, I can see that it is exothermic, since the temperature increases of the calorimeter. And so when I fill it in, I would go 30 plus 20, since we're assuming the density of water, which means that 1 gram is equal to 1 milliliter, then the milliliters are the same as grams. So writing that in here, and we're going to put 4.19, and then the temperature change is 28 minus 21. Now, for the moles here, since what we want is the molar enthalpy of neutralization for sodium hydroxide, then we can find this moles, given that we have a concentration and a volume, we can use C equals N over V in order to isolate for the moles. And this would be for the sodium hydroxide. And so now, plugging that in here into our equation above, we have 0.020 mole multiplied by your molar enthalpy of reaction, which we don't know yet, but we're going to isolate for it. And then we're going to multiply our terms together here on the right side so that we can get our enthalpy change from the calorimeter. Now, we're going to have to convert it to kilojoules. So when you multiply all of that here, remember you're going to end up getting joules. So divided by 1,000 to get kilojoules. And when we do that, we end up with minus 1.4665 kilojoules. So now I'm going to divide both sides by the moles here. We end up getting a molar enthalpy of reaction for the neutralization of sodium hydroxide of negative 73. And since we want 2 significant digits, it'll be 73 kilojoules per mole. Now, if you're having any suspicions or reservations about the authenticity of these calorimetric calculations, they're probably valid and right. And that's because to do these calculations, we actually make a couple of assumptions with our calorimeter. The first assumption is that none of the heat from the reaction gets transferred to the can itself or whatever is holding the solution that is heating up. And that's because we say that water having such a high heat capacity is going to absorb most of the heat anyway, and any trace amount that goes to the can that's holding the water would be negligible anyway. Secondly, we say that any solution or the solutes that are in the solution, the heat that will get transferred to them is negligible as well. And that's because they're mostly water. So we do make the assumption that solutions carry the same specific heat capacity as water and the same density as water. Now, that is not technically correct, and we do have ways that we do account for this. But for the assumptions that we're doing, or for the reactions that we're performing here, these assumptions work relatively well.